Let's discuss the most important sorting algorithm, that is merge sort. So this algorithm is widely used for the sorting. In fact, 98% of the time we use the merge sort for sorting an array. So let's try to understand this with the help of example. Consider this is the unsorted array, that is an integer array that is given to me as an input, and I need to sort this integer array by using the merge sort. So in case of merge sort, we use the standard approach, and the algorithm that we used here is divide and conquer approach. So what is this divide and conquer approach? Basically, we start dividing this unsorted array into the two equal parts of an subarray until we left with the single element in each subarray. So what that means? It means this is the unsorted array that is given to me as an input, and I need to keep on dividing this unsorted array into the two equal halves until we left with the single element in each subarray. And this process we call it as a divide process. So let's first understand how this divide process works. So this is the unsorted array and we divide that into the two parts. As you can see, this is my left subarray and this is my right subarray. In my left subarray we have the 4 elements, and the right subarray we have the 4 elements. Total we have the 8 elements here. Please note the index here. In the left subarray we have the index from 0 to 3, and in the right subarray we have the index from 4 to 7. Please note one point, we are not dividing this array, but we are simply noted down these indexes. These indexes tell me that from which particular point we are dividing this array. So let's first start dividing the left subarray. So we again divide this left subarray into the two parts. This is my left subarray, this is my right subarray. Here we have the two elements, here also we have the two elements. So its starting index is 0 and index is 1, and here starting index is 2 and end index is 3. Now we can do further division. So let's first divide the left one. So I divide the left one. Now we left with the two subarray, and each subarray has the one element only. So in the left subarray we have the number 8 and the right subarray we have the number 4. As we told in the definition that we need to keep on doing this division into the two equal halves until we left with the single element in a subarray. Now here we have the two subarray and there are only single element. It means I need to stop my division here for this subarray. Let's move to this one. Here also we divide that into the two parts, and here we have the single element into this two subarray, that is 3 and 12. Now the same process we repeat for this right subarray also. So here we have the two subarray of two elements each, and then correspondingly we have the single element in each subarray. And now this division process is completed. Why? Because in each of this subarray we just left with the single element. So this is the division process. Let's see the time complexity of this division process. So in the division process, in every level we are dividing the subarray into the two equal halves. Like if I consider this particular level, we divide this complete array into the two subarrays. So here we have the two subarray in this division operations. Similarly, if I move to the next level, in this particular level, total number of subarray that we have is 2 to the power 2, that is 4, 1, 2, 3 and 4. So in this level we have the total 4 subarrays. So we have the first division operation here, then in the next level we have again another division operations. Now similarly, how many number of subarray we divided in this level? So total we have 2 to the power 3. So there are total 8 subarrays in this level. So now let's say the number of elements in this array can be anything. Like here we have the 8, but actual scenario the number of elements in an array can be anything. So let's assume it is a n. Now if the number of elements in this array is n, so we can assume this division process will go until k level, and then total number of subarrays in the kth level will be 2 to the power k. So in that scenarios we need to perform this division operation k times if we have, let's say, the number of element is n. In this case we just have the 3 division operations, but if the number of elements can be anything, it can be n also. So in case of n, we have to perform the division operations kth time. This is the first division, this is the second, third, and so on till k. And this k is actually predicting the number of times we are performing the divisions in every level. It means how many number of levels are there. So can I say 2 to the power k equal to n? Why? Because at this kth level we have the different subarrays, and I'm sure in that level, in every subarray we just have the single element in each of these subarrays. It means that must be equal to n. That is the number of elements that is present in this array. So that's why 2 to the power k equal to n. Now let's apply the log base 2 in both the sides. So now we have k equal to log n. And can I say that this log n is nothing but the O of log n time complexity. It means in this division process, we are taking the O of log n time to divide that into the different subarrays of single element. Now let's see the merge process. So in the merge process, we simply compare the two equal subarrays and store the element in the sorted format. Like in this case, we have the two subarrays, and this is my left subarray, this is my right subarray, and we just have the one number in this. It means these two subarrays are already sorted. So we simply compare these numbers. So 4 is less than 8. So we store the numbers into the sorted format into the main subarray. So now in this subarray we have 4 and 8. 4 comes at the index 0 and 8 comes at the index 1. And this happens after comparison between these two numbers in these two different subarrays. Similarly, we compare the numbers in these two subarrays, and whichever is less come at the index 2 and more comes at the index 3. Same thing we have to do for all of these subarrays. So after this comparison, now we have these four subarrays, and each of these subarrays having a two numbers. So now we have the two equal subarrays, and both the subarrays are sorted individually. So this is also sorted and this is also sorted. And now we need to compare all these numbers with all the numbers in the other subarrays. So it means total 4 comparison required in this case to make a single subarrays having a 4 numbers after this 4 comparisons. Similarly, in these two subarrays also we required the 4 comparison because we have the 4 numbers here, and then we create a single subarray having a 4 numbers sorted. So this is the merge operations where we need to compare the left and right subarray. So if you see in the merge process, we perform comparison with all the element in the array. So in the problem, if we have n elements in the array, then we need to perform the n comparisons to perform these merge operations. Because eventually when we create one single sorted left subarray and sorted right subarray, then again we need to compare all these numbers and create a final sorted array. So it means in this merge operations we have the O of n time complexity because we need to compare every number during the merge process. So now in the merge sort we have overall n log n complexity.